half of it, and the other one is something that we'll do completely. The first one হচ্ছে to find the distance of a star, the temperature of a star, and the size of a star. এই তিনটা জিনিস আমাদের বের করতে হবে. So we came across a formula earlier, which is called a quantity called luminosity, and luminosity is L equals to 4 pi r square sigma t to the power 4. This is the equation for luminosity. Luminosity happens to be the watt of a star. Luminosity হচ্ছে what quantity of a star? Power. Okay, so the power emitted by a star, or energy emitted per second. R is the radius of the star, so this is how big the star is, and T is the temperature of the star, surface temperature. So আমাদের এই তিনটা জিনিস বের করতে হবে. Okay, now there was a problem that we faced last class. যেটা হচ্ছে you can't say how big a star is until you know how far it is, right? Because distance ছাড়া হচ্ছে না. So we needed to find the distance, and distance এর জন্য there are many different ways of finding distance. So on the syllabus, they just focus on one of them. It's for far away or very far away galaxies. So আমরা কিন্তু হচ্ছে যে ডিসটেন্সটা ইউজ করব, যে প্রসেসটা ইউজ করব, it's not applicable for stars. It's only applicable for galaxies. And very far away galaxies appear as what to you? Just dots. Okay, so এটা কেমনে বের করতে হবে এটা একটু দেখি. So এটা বের করে রাখলে there is this word that's thrown around in your syllabus a lot. It's astrophysics সব জায়গায় use করে. It's called the standard candle. So what's the standard candle? It's called the standard candle method. I talked about this last class. So what's the standard candle method? So standard candle হচ্ছে nothing to do with astrophysics. Standard candle actually came from a very random source out there. Standard candle is actually a remnant of navigation. Back in the day, যখন navigate করতো sailorরা, তখন তারা একটা জিনিস use করতো called standard candle. What is this, right? So let's see how standard candle is used in navigation. তোমরা যদি এটা বুঝো কেন navigation use করা হয়, you'll understand better why we use it in astrophysics. Okay, so let's get back to navigation এর সময়. What's the standard candle's purpose? So let's say this is early 1800s, and sailing was very common. Like, ships were used to travel across the world, and this is let's say a ship out in the water, and it's nighttime. So listen carefully. It's one of those old ships out there. So it's nighttime right now, and the ship wants to know if it's near this rock or not. To know that, what do they use? Do you know? When you're in a ship, right, and you want to know if you're close to the shore or not, right? What is it that they used to use? Sound. Who made the sound? Speaker. Horn. Mic. Oh, like the Vikings. That's actually true. But that is only valid if the person who's making the sound is aware of you. Well, let's say you're sailing, you're a new person, you come into this new land here, right? And you have no clue where the shore is. And then it's nighttime, and your ship is going full sail, right? You'll hit rocks, and that's the end of you, right? So how do you during nighttime allow people to know that there are rocks here? Oh no, this is 1700s, like the pirates. So there could be now we obviously use it now it's super modern. I mean, you have sonar, radar, night vision, A vision, Y vision, walkie-talkie, everything is out there, right? But now it's difficult to hide yourself. That's what submarines have to do. They go underwater and they stay silent, right? But back in the day, you're in a ship and you're sailing, right? And you're next to a coast, and there happens to be a cliff, and if you hit that, that's the end of you, right? It's full pitch darkness, zero light out there. This cloudy, there's no star. You don't know which is north, south, and there's no moon, so there's zero light out there. The only thing you see is darkness, and the only thing you hear are the waves in the ocean, right? How do you know there's a cliff in front of you? Oh, you mean like a torchlight in front of the ship, like a headlight? Yeah, that's fine. Like, somebody holding like a hurricane. You'll know about the cliff the moment you hit the cliff. So back in the day, even 1900s though, the reason why Titanic sank is because they didn't know there was an iceberg in front of it. There was this one guy whose job was to be up there and look for icebergs. Oh, দেখতে পারেন নাই. That's it. The whole ship went down just because he couldn't see it, right? So what's the solution out there? Online, there are some answers. Flashlight. Yeah, so it's 1710. This is the year. So flashlight এখন invent হয়নি, unfortunately. Yes. So normally when you're coming very close to the shore, you'll hear waves crashing. That's one thing, right? But there was a much easier answer, and I think one of you mentioned it. Lighthouses. You use lighthouses. Lighthouses. I know that some of you don't even know what these are. Like, you probably think that's decoration or something. But back in the day, lighthouses were life-saving. So especially like UK আশেপাশে যে জায়গাগুলো, those were very rocky cliff areas, right? So এখানে কি করা হতো? They used to set up a lighthouse, and lighthouse এখানে একটা lamp থাকতো. And what would the lamp continuously do throughout the night? Just beam out light like that, right? And এই লাইট গুলো অনেক দূরে যে দেখা যেত. So there's light coming out from it and it's moving around. এখন তো move করে, আগে move করতো না. There was this light coming out from every side, right? How would that help the person know about the cliff? So as a person sailing, একটা ছোট light দেখা গেল, what could that be? Most likely a lighthouse. So that's an indicator that there's a shore out there. You get my point? But there was a problem actually, which was eventually fixed, right? People usually never collaborated back in 1700s. Empires chilo, no one really bothered with anyone except for one thing they collaborated. It was navigation of seas, because the Dutch, the English, the Spanish, they just went to every part of the world, just to conquer them. So we're at a common navigation system anchilo. So imagine you're in a ship and you see a light out there, okay, and you're sailing straight ahead at it, like only dim. What would you think is the lighthouse? Is it very close or very far away? Far away, right? And you're going full speed because it's not sure yet of it. Suddenly you crash into the wall and you see it's a candle. Like, it's a small candle. You didn't know it was a candle. You thought it's a lighthouse. Light na. Bright light, but it was actually what? A very small light. And where was it? Right in front of you. So isn't that a problem? So there's a judgment error here. Candle chilo. Or on the other hand, somebody's using like this super bright light, right? And ওটা অনেক bright দেখা যাচ্ছে, and this person is thinking it's very close to the shore. But যাচ্ছে like the same way. So what does it mean? It's very far away and it's very bright. So what's the issue here? The issue here is that everyone's candle, again, candle use করতো, is of what brightness? Different brightness. So as a sailor, আমার তো জানা দরকার that candle is like what size, what brightness. Then I can make my judgment, right? So eventually they decided 1700s at the year that all lighthouses, especially the ones that were ruled by the UK, ওদের প্রত্যেকটা lighthouses ভিতরে they used a candle that was the same shape, size, and everything. And that's what is referred as the what candle? The standard candle. We can take ashlo. So the standard candle is a candle whose what do we know? Power. That's the main thing that we have to take away from here. A standard candle is literally a candle whose what do you know? The brightness, right? So act a navigator, like the captain of a ship, standard candle kirokom brightness is like just memorize for him. He can always look at it and figure out what to do with it. Because korte অভ্যাস হয়ে গেছে, right? So that's called standard candle. Now that you know the power, wouldn't you be better at making a judgment if it's close or far away? Because now you know how bright these are supposed to be. Exactly same mechanism আমরা কোথায় use করি? Space if I want to know how far something is, I need to know what of that object. It's brightness, it's standard power. And last class, I think I told you, the things that we see in space, most of them are key problem, that we don't know how far they are. And because we don't know how far they are, we can't make a judgment. Did it keep big or small, far or close, right? But there are few things out there, যাদের brightness and power and everything আমরা জানি. What are those? I gave you two of them. একটা বললে চলবে. Can you tell me what object in space do we know the power of? Sun, yes, but sun to সব জায়গায় নাই. Yeah, what was it? Supernova. And then the supernova can happen where? Anywhere. And the supernova happens in such a way that the power given off by the supernova is always going to be what amount? Same. That's what supernovas are. So supernova কি হিসেবে consider করতে পারি আমরা? A standard candle. Because now we know that a supernova is going to be of this brightness, and then I see it's very dim. What does that tell me? Very far away. I see it's very bright. what does it mean? It's very close because I know the standard value for it, right? So আমরা যেটা করি, we wait for a what to show up in one of these galaxies that we are pointing at, a supernova. And the moment you get a supernova here, you know J supernova, and this part is very important, listen carefully, okay? You know this supernova that has been formed here is supposed to have a power of, let's say, 1 into 10 to the power 70 watts. That's the power of a supernova. That's what we know. But Earth, so you see this as something like 1 into, so this is Earth telescope point kora. Telescope to light pick up korlo, and the power that you see on the telescope is 1 into 10 to the power minus 36 watt. What does that tell you? That the power was this and the power became that, right? What's the reason for the reduction in the power that you're seeing? Distance. And there's an equation that relates to how much the power will change due to distance. What is that formula? Luminosity or intensity, intensity daki, by the way, the one that you find on Earth. Intensity is equal to L divided by 4 pi d square. And that d that you see there is the watt between you and the telescope, the distance, right? And from there, we can make an estimation. And that's how we find distances of faraway galaxies out there. A galaxy just dots that I'll show you actual pictures of it. They're like very small. You can't actually individually find stars in them because at the galaxy, that's a galaxy, right? And how many stars are there? 1 trillion plus stars out there, but it looks like a what for you? A blob, because they're so far away that it looks like really small. Now, once you're looking at this, there's like a bright spot here and it disappears. That's a supernova. And then we can figure out how far it is, okay? But then I think I told you last class that supernova, wait for is going to be a long wait, right? So there are other things that we know power of. And one of them is called a Cepheid variable. CEPHEID variable. It's a star that pulsates. So let's say you're looking at a galaxy like this. Our galaxy মধ্যে এখানে একটা এইটা আছে তোমার হচ্ছে pulse হচ্ছে আসে যায়. What does that tell you? It's a pulsating star, right? It's not a pulsar, by the way. Pulsar are different image. It's like a normal star, but the brightness kome bare. It's like a breathing effect. And if you know the time it takes to do the cycle of bright to dim to bright, you can actually find the watt of this thing, the power. There's a mathematical equation for it. And now we can also find distances of galaxies by finding the watt in them, a Cepheid variable. So all these things whose power we know beforehand are referred as what? Standard candle. And that's one of the most common questions that has come so far. Pasta paper modde, I think chapter modde question ta, what's the standard candle? So what's a standard candle? It's an object in space whose what do we know? Power or luminosity. Okay, that's what standard candle is. Astronomical sense, that's what standard candle means. Right. So why is it considered a standard? So supernova so why is it? No, so the reason why a supernova is considered to be a standard candle is because supernova আমরা কি জানি? Power. Supernova কি সব জায়গায় হয়? না তো, there are galaxies যেখানে supernova আমরা কোনোদিন নাও দেখতে পারি. It's just our bad luck. Or it's a very newly formed galaxy. Newly formed galaxy তে a star form হবে, star বড় হবে, red giant হবে, red supergiant হবে, then collapse onto itself and then form a supernova. কিছু time দিতে হবে তো, right? It can't happen whenever you want. So তার জন্য হচ্ছে it's not possible for us to find the distance of all galaxies using this method. But there's a good news. There's actually a method that we know that will help you find the distance of anything in space. And then standard candle লাগে না, ওইটা পরে আমরা জানতে পারছি. This was how we first found it. যখনই আমি ওই মেথডটা বলি, students go like, then how did we find it first? মানে first থেকে আমরা বের করছিলাম. So first এইভাবে বের করছি using standard candle, and there was another method called the annual parallax. তোমাদের syllabus ওটা নাই, okay? And the method that we're going to use that like finds distance of anything in space is called the Hubble's law. There's a formula V equals to HD. It's a IGCSE syllabus O-level syllabus. Or V equals to HD there, you can find the distance of anything in space if you can find the watt of that thing in space, the speed at which it's moving. And how can you find the speed of objects moving in space? Doppler effect. Remember Doppler effect is so that's the last part of our chapter. Okay. So yeah, now that I know the distance of my object in space, আমি কি করব? I mean, distance use করে I can actually find the watt of that star, luminosity. And I'm using luminosity jani, and I know temperature. What can I find? The radius and the size. But how do we know the temperature? Temperature to kotha kono bola hoy nai. So that's what we're going to do right now. Okay. So tar agde, are you okay with standard candle? Is there anything that you want me to clarify? Right, good question. So supernova is an event that takes place when a certain type of star collapses. And those stars that collapse because of their own gravity, they have to reach a certain size and threshold for that to happen. And gravitationally speaking, in terms of radiation pressure and gravitational force balancing out, if you go beyond a certain size, you'll collapse. There's a critical mass bola hoy. So we take the critical mass and we just convert the critical mass into pure what? Energy. And that's how we know the energy output of a supernova, the power of a supernova. And then the reason why it's easy for us to do that, because we know what mass stars go supernova. So that we know the mass, we know that the mass turns entirely into what in a supernova? Energy, right? So the energy they are able to play what power it should be. The power no, so there are different types of supernova, A, B, C, different alphabet. They depend on what kind of star they became supernova from. So is it like a red supergiant that became a supernova, or was it like a blue giant that became a supernova? They can happen in different stages. The power output is different for each of them. Oh, we can see their wavelength. So when the stars are out there, you can see the color they're giving off. That's what we're going to do today. Like, why do stars appear red and blue? Because they're actually all giving off the same color, but they appear red and blue sometimes, right? Can we tell? Amongst one billion stars, these stars will supernova and the right, that's what I said last class. I think I told you about the intern who works to find supernova. So back in the day, it was very difficult. So তার জন্য দেখা যেত যে once in every 2-3 years একটা supernova পাওয়া যাচ্ছে. এখন it's very easy. You have your telescope pointed to the sky in a region, let's say some place there are a lot of galaxies out there, and the computer is just focused in there. If there's a subtle change in brightness in any part of the pixel in the screen, the computer like alerts someone, and then the person comes and sees what is it. It could be a supernova, it could be a pulsar. It's like this thing that pulsates gamma radiation. It could be just an anomaly. It could be some random impact in space, right? Talking about filter what a supernova out there. So now it's mostly done by computers. You don't need to manually do it. So they just point telescopes at random places, and supernova actually because there's so many galaxies out there. Okay, I'll show you an actual supernova and capture. Okay, so this is sorry. Oh no, the universe also has a critical mass. Everything has a critical mass. ওই massটা যদি cross করো তাহলে gravity takes over. So ওই gravity যখন take over করে তখন হচ্ছে it collapses upon itself. Yeah, it's based on the observations we have made. So right now it's wrong. The reason why it's wrong, there's a reason why it's wrong. It's because we underestimated the mass of our universe. Now we know the universe has more mass than we predicted, and that's due to a thing called the dark matter. And we now know 86% of our universe is filled with this mass that we can't detect, but we know it's there. Its gravity is there. So the critical mass has changed a lot over the years. Previously, we thought the universe can collapse very soon, but now it has more gravity. So the way it's going to expand is going to be different than what we thought earlier. Right, so I know it's not what you'd imagine as this big explosion or anything, but that's a supernova, real supernova caught on telescope. So did you see that bright dot out there? Now, it's just a dot. It's a supernova. Apparently, it's the most violent event in the universe, right? You have to understand it is outshining a galaxy. Just look at the entire galaxy and look at the dot, right? It's something that took place in that galaxy that outshines the entire galaxy, which means it's obviously a lot of energy from it, right? So yeah, that is what a supernova looks like. There আশেপাশে যদি কোনো star supernova যায়, right? We won't survive. Like, the whole Earth will just vaporize, and we believe it has happened before because there are layers of crystallized soil across the Earth. একই জায়গায়. If you keep digging deep, right, you'll find a layer again. It's crystals. Crystals can only form under what temperature? Extremely, extremely high temperature. And we have actually found it everywhere. So there's a understanding that somewhere nearby, like, a few billion years back, a supernova went off, and radiation passed through the Earth, right? Actually crystallized the surface of the Earth. And then the Earth cooled down later on. So crystals go underground. So it's there. This is the evidence for that, right? Right now, there are no candidates for a supernova nearby. Only Betelgeuse or Betelgeuse 600 light years away. ওইটা is the one that's the biggest candidate. Okay, but ওটা কিছু হলে আমাদের কিছু হবে না, it's very far away, 600 light years. Okay, so let's move on. So there's an equation for it, like the rate at which they change. It's why do they pulsate, by the way? It's something you could have understood in all levels, because remember there was something called the radiation pressure that pushes the star outwards, and there's something that keeps the star going inwards, like gravity. And at one point, what do the two forces do? They balance out, and the star becomes what? Stable. Some stars, right? The core is not consistent in the production of its energy, so it dies out. And as it dies out, the star collapses. As it collapses, the pressure and temperature rises again. And then again, it goes out. But it can't sustain that. So it keeps doing that. And I think somehow mathematically they figured out the power it should be given off for that to happen. Yeah. Yes, correct. Because at one point, the expansion can't be sustained. So the thing will fall back onto itself. Like a balloon bursting, right? ওটা কিন্তু critical mass বলে না, ওটাকে critical elasticity বলে. So balloon ফুলতে ফুলতে একটা পয়েন্টে burst করে না, কেন burst করে? There's a elastic limit that you cross, right? ওই elastic limit for the universe is based on the mass of the universe. There was a speculation out there, but it's proven that it's impossible. So universe collapsing and falling back is called Big Crunch, the event. ওটা how possible নাই. Now we know it's not possible. Back in the 80s, we thought that was it. The universe expand করতে করতে our collapse করে, our expand করে, our collapse করে, it keeps going on. Now we have evidence that it's not possible. There's not enough gravity out there to bring the universe back in. So it'll only expand. আচ্ছা, টেম্পারেচারটা দেখি, তারপর হচ্ছে I'll put everything together. এখানে তিনটা জিনিস করতে হবে, তো সো তিনটা আলাদা করে করা, তারপর তোমাকে একসাথে দেখাবো how to bring these things together. Okay, so how do you find the temperature of a star? So একটা star আছে তোমার এখানে, and you want to know how hot the star is, right? How do you find that? So what can we do to find the temperature of a star? Now you do understand the only information we get from a star is what? Intensity and the wavelength. And these waves are kichu na to, right? So apparently using that, you can find the temperature of a star. Now, can you tell me on Earth, if I ask you to find the temperature of something, right? What would you use? A thermometer, right? A thermometer measures the what of that object? Internal energy. That's thermometer device will pick up some internal energy, and that's how it works, right? But there's another kind of thermometer out there, the one that picks up what from a person? Radiation. It's called an infrared thermometer. মাথার কাছে ধরলে tells you temperature, right? That picks up infrared waves from you. So we thought যে waves থেকে the temperature কিছু তো পাওয়া উচিত, right? Then we looked at infrared radiation coming from our stars, and it was not actually matching the values. And the reason behind that is the infrared radiation that's traveling is losing what over time? Intensity, energy, right? তার জন্য answer to পাওয়া যেত না, because it's obviously going to be cooler than what you expect, right? So তুমি যদি একটা infrared thermometer একটা star দিকে point করো, right? What are you supposed to get the temperature of? Earth's temperature, because there's so much other material in between, right? So it didn't really work out. You go to space and do it, কিসের temperature পাবা? Space temperature পাবা, not the star's temperature. You get my point, right? So how can we find the temperature of a star? So এটা করার জন্য we took inspiration from thermodynamics. So যে জিনিসটা হচ্ছে দেখাবো এখন is actually part of pure thermodynamics. তোমাদের নাই এটা, but it was used in thermodynamics. So back in the day when people were working with radiators, remember dull, dark, rough surfaces are good absorbers and radiators. Back in that time, যখন এটা কাজ করতেছিল, somebody proposed that there's this hypothetical object out there. It's the best absorber in the universe. মানে এটাকে তুমি যা হিট দিবা সব নিয়ে নিবে. And because it's the best absorber out there, it will also be the best what out there, emitter out there. And এটা হচ্ছে একটা hypothetical thing. The person came up with this idea, and it was called the black body radiator. So black body radiator হচ্ছে তোমাদের question জিজ্ঞেস করে, what's a black body radiator? It's an object that has 100% efficiency in what? Emission. So তোমার যে energy থাকে সব ছেড়ে দেয়. That's called a black body radiator. এটা কাছাকাছি কিছু exist করে না on Earth, okay? Because there's nothing that gives off all its energy, because everything has its own internal energy, right? So the black body radiator was out there. Why did the person come up with this? Because he came up with a solution. He said that if an object is a black body radiator, তাহলে there's a relationship between the wavelength of the light it emits and the temperature of its surface. And তোমাদের syllabus এটাকে constant বলে, constant আমি বলে দিচ্ছি কত, 898 into 10 to the power minus 3 meter Kelvin. Okay, I don't know কেন ওরা তোমাদের ভ্যালুটা দিচ্ছে না, ওরা তোমাদের just ratio করে ম্যাথটা করতে বলে। Anyways, lambda t equals to 2.898 into 10 to the minus 3 meter Kelvin. আর এই lambda এখানে একটা ছোট প্রিফিক্স থাকে, like max, মানে subscript. So এই max টা কি একটু বুঝাচ্ছি। So first of all, what is this equation telling us? This equation is telling us that if something has temperature, it will give off what from it? Radiation. And with radiation or wavelength, will tell you how hot this is. But this equation only works for what material? A black body radiator, which doesn't really exist out there. So can I use this to find the temperature of the lamp in the room? Absolutely not. It's not a black body radiator. So যদি এটা apply করে দেখো যে full temperature দিচ্ছে, right? So that was out there. The idea was there. কিসের জন্য একটু বলি context day. If you take a rod, like a metal rod, and you put it in a flame and keep it there for some time, and you take it out, doesn't it glow? Like a metal rod. The person was actually trying to see that the glow can over a red can over, and he found that the redness is due to the temperature. And if you know, the hotter the object becomes, red take a cone color shift over blue, and at a point they were white. That, like, you know, have you seen the flames in a stove? Blue flame hoy majhe majhe, orange hoy, yellow hoy, candle er moddhe different thake. Ogla to hoy because of incomplete combustion, and because of that the temperature varies. Blue flame is hotter than red flame. That's just a fact, right? So temperature has something to do with the wavelength. So the person wanted to figure that out, and he stumbled upon this equation. And for many years, it nothing is black body radiator out there, until somebody thought, wait a second, what's the criteria for a black body radiator? 100% efficiency in emission. That sounds very similar to a what? A star. Because if you think of a star, একটা স্টারের টেম্পারেচার সারফেসে কিরকম হয়, like what's an average temperature of the surface temperature for our sun? It's not very high, by the way. মনে হবে অনেক গরম. We actually sent a satellite recently into the sun. Do you know that? Yeah, so it's not really that hot. Our satellite survived. It didn't crash into the sun, by the way. It's just atmospheric pressure. It's 5,000 Kelvin, 5,500 to be precise. That's the surface temperature of the star, like our sun. This is actually cooler than filament lamps. Filament lamps go up till 7,000 Kelvin. It is 20 times cooler than a lightning. Lightning temperature is 10,000, 15,000 degrees Celsius. It's much cooler than that, right? So it's actually a very low temperature out there. But what is the temperature of the space around it? I mean, last class, I think you answered it. 3 Kelvin. So if your object is 5,500 Kelvin, and it is in the vicinity of 3 Kelvin, when it's in 3 Kelvin, what your object would start to do is it will start to radiate heat out, because of temperature difference. And your object is 5,500 here, and space is almost zero out there. How much energy does your object eventually intend to get rid of? Almost all, because you have to go down to 0 Kelvin in order to cool down, right? So wouldn't that eventually mean that the star will give up all its energy? And that meets the criteria for a what object? A black body radiator. And we thought, okay, wait a second, let's see the colors that's coming from a star and apply this. And yes, it actually worked out. Once we took the wavelength from our sun and we placed it in this equation, right? We actually got the temperature as a confirmation, 2.898 into 10 to the power minus 3 per A. We found the T to be 5,500 Kelvin. And this equation basically tells you that the wavelength of a star is what to temperature, inversely related. And এটা নিয়ে তোমাদের বেশি question করে. So let's go back to our O levels. Do you remember there was something called a red giant? Can you tell me a couple of features of a red giant compared to a normal star?
It's cooler than
Yeah, it's actually cooler. Is it at the world size that the energy dissipated is spread over a large area? It actually cools down. Okay, and it's extremely big. Sun jodi super red giant hoy, I think I've shown this before. I think this context is important. So this is a red giant. Okay, our sun again red giant hoy. If that's the red giant that our sun is, right? What's the size of our sun right now? Small dot. Yeah. Actually, not borona. Yeah. There. Okay, so do you see that small yellow dot out there? That's our sun right now. One day in the future, 4 or 5 billion years from now, it'll actually get this big in size. It'll become so big in size that its size will actually engulf the orbit of Mercury, Venus, and almost Earth. Some estimates tell that it'll go beyond Earth as well. the sun, the size of the sun. Okay, so it's called a red giant. Now it's a red color can. So the red color is because its temperature ki onek low. Temperature low hole wavelength ki hoy onek beshi hoy, and longer wavelength tends towards which color? Red, right? Similarly, there are stars out there called the blue giants, like blazing blue stars out there. What do you think their temperatures are? Very high. Okay, they're some of the hottest stars out there in the universe. Their wavelength is অনেক short. Their temperature অনেক high হওয়া উচিত. Their temperatures go around 10,000 Kelvin. You get my point? That's the reason why things appear reddish and bluish. But there's a small issue. Issueটা হচ্ছে যে max-টা দিয়ে. Do you know what the colors would look like from the light that we get from our sun? The sun-এর যে লাইটটা বের হচ্ছে ওটাকে যদি আমি plot করি না graph, right? What do you think? It's intensity, watt per meter square, and this is lambda, the wavelengths that our sun is providing. Can you tell me what colors the sun gives off? All the colors. It's the whole spectrum with a catch, though. What's the catch? Yes, but then there's another catch. Yes, very good. Some colors are missing because our sun produces a what spectrum? Yes, absorption spectrum. It produces all the colors with certain colors missing in it, right? So that's the reason why I think 1700s when Newton was working with the prism, right? He stated something. He took the light from the sun, he passed it through the prism, it fell on like a surface. He looked through the microscope and he spotted what in the spectrum? Dark lines. And he thought it was a imperfection in the crystal of the prism that caused it. Now we know what he saw was actually what? The dark bands that correspond to what? Hydrogen. Hydrogen is a spectrum, right? So it's supposed to give you what color? The whole spectrum. What do you think a red giant will give off in the future? What color? It actually will give the exact same thing. It's still burning hydrogen, right, in the surface. You're still supposed to get hydrogen spectrum. But then why is our sun yellow, white, and red giant red? So the reason behind that is this. So if you look at the graph generated for the different colors out there, we find that the peak color varies with temperature. So if your wavelength is very short, right, it means you are what star, very high temperature star. তুমি যদি এখানে পিকটা দেখো, I'll show you with a better diagram in a minute, but তুমি যদি পিকটা দেখো, এই পিকটার যে ওয়েভলেন্থটা এটা আমরা ম্যাথে ইউজ করি, তার জন্য এটাকে আমরা কি ডাকি? Lambda max. The max is not the lambda's max, it is the intensity's max. So the lambda max corresponds to what? The lambda at which you have maximum intensity, and that fluctuates because of temperature. So you'll find that cooler stars have a lower lambda max. Sorry, ulta hoye jamon na eta diye jabe eta here. আমি color scheme দিয়ে দেখাতে easier হবে বুঝতে তোমাদের. But the point is that the lambda max varies because of temperature. At the end of the day, what color are all the stars giving off? Same. They're giving off the full spectrum. Is that within the spectrum, certain colors are what? Bright and dim. I went through this example maybe before. The tube lights that you see in this classroom, right? They're supposed to be all white. But if you look at them, they're different shades of white. What's different about them? Yeah, they have different tones, like warm and cool and everything, right? So if something like the tube light there, the one, it's a little bluish, but it's a white color with bluish hue to it, right? What does that mean? Yeah, it's given off all the colors of the spectrum, but which one is more? Blue. Blue is more intense, right? And something that's a little yellowish, right? ওইটা মানে হচ্ছে সবই দিচ্ছে, but which one is more intense there? The yellow. And that's how you create warm lights and cool lights out there. Similarly, when you're looking at a star, right, it's actually given off all the colors of the spectrum, but it appears bluish because what color is more intense in that spectrum? Blue. And if blue is the most intense color in the spectrum, it means it's a what star? A hot star. Okay, and যদি red হচ্ছে the most intense, it's a cool star. Yes, বলো. No, these are not BlackBerry radiators, so that doesn't work. So yeah, students will try this. They'll try to take the wavelength and figure out like the temperature that have mathematically 10,000, 15,000 blue J2. But that's not a BlackBerry radiator, so it's not even close. Okay. So yeah, the spectrum looks like this. Okay. So I'll show you an animation as well. So do you see that the max changes? So yeah, this is a low temperature star. The higher temperature, how the temperature changes. So the peak value change. But they're all given off what colors eventually? all of them, ultraviolet, infrared, visible light, সবকিছু, okay? এইটাই তোমাদের কি হচ্ছে আমি এই জায়গায় দেখতে চাইলে better বুঝবা। Stars of the same color or same temperature. Yes, it's true. So stars temperature don't vary much unless they're a different type. So there's something called a main sequence. Do you remember the main sequence? So the main sequence stars have like a range of temperature out there. That's why they're all the same type of color with some hues with them. Right, so look at this. You have the spectrum here. So আমি হচ্ছে এই পাশে Earth-এর এটা দেখি. So can anyone tell me why can't we use this logic, right, to find the temperature of a planet? Right, it's not a black body radiator, but you see night sky planets are brighter than stars. Right now কিন্তু অনেকগুলো planet দেখা যাচ্ছে. So if you see Venus, if you see Jupiter, Saturn, সবগুলো দেখতে পারবা. They are mistaken almost always as what? Stars ever দেখা যায় না, stars barely দেখা যায়, আচ্ছা? So why can't we use black body radiator equation to find the temperature of the star or that planet? Not 100% efficient, right? But do you know if you did try, what would the answer be? The same temperature as our sun, because the light that you see is the light of the sun that's being reflected. The planets don't glow, planets reflect, right? Mooner jonno korleo erokom দেখা যাবে, because you're basically getting the light from the moon, which is actually whose light? Yeah, so that's the reason why we can't do this for the Earth or planets. What if you do it for light bulb? So light bulb যদি দেখো এই কিছুই দেখাচ্ছে না, because light bulb is again what? Not a black body radiator. Once you go to the sun, that's when you get this thing. And sun-এর peakটা দেখছো কোন জায়গাটায়? It's in the green, cyan, yellow part. এই তিনটা যখন বের হয়, the sun appears green. Cyan, yellow, no, right? It's a mixture of all three. What would that be? Yellow white. So that's the color our sun is, yellowish white. And let's zoom out. Now if I go to Sirius A, it's a blue giant if I'm not wrong. So if you go to Sirius A, you'll find that it's a massive star out there. So I'll give all the values here. And its wavelength is really short. So what does that tell you? It's a very high temperature star. Its temperature is 10,000 degrees Celsius or Kelvin. So that's how it changes. So তোমরা একটা জিনিস নোটিস করবা, as temperature decreases, so as temperature increases, দুইটা জিনিস হয়, wavelength decreases and what increases? Intensity. কেন intensity বাড়ে? আমি আবার রিপিট করে দেখো, আমার যখন হচ্ছে wavelengthটা কমে যাচ্ছে, লেফটে যাচ্ছে, দেখছো পিকটা বড় হচ্ছে, and the peak increases like that. So why is intensity increasing if your wavelength is decreasing? Right, more temperature. So good catch. More temperature means more intensity. Why? More power per radio. The kinetic theory of matter থেকে না বলো? Yes. Okay, আমরা আজকে কি করছি তার জন্য I thought যে relate করতে পারবা এই that. What's the last quantity in this equation? Temperature. So temperature বাড়লে একটা স্টারের কি বেড়ে যায়? Power. That's why intensity বেড়ে যাচ্ছে. That's why they appear brighter. Okay. So yeah, there you go. This is how you find the temperature. So now let's bring everything full circle. So এই equationটা যদি আমি বের করতে চাই এখান থেকে একটা স্টারের হচ্ছে power, I can find temperature using what? The equation I just shown you. And I can find the radius by finding the distance by using the standard candle. And by doing so, we can find the luminosity, right? এটার নাম আছে একটা এই lawটা. This law that we just use here, this one, is called the Wien's displacement law. Wien's displacement law. And what does the law state? It's a question that you get. The law states that the wavelength of the maximum intensity light is inversely proportional to the surface temperature of a star, provided that we assume the star is a black body radiator. Okay. Right. So that's actually the first two topics. Last O-level sector recap. So if you have understood things here or not, I'll give you the notes. But actually quite self-explained. Understand term luminosity as the total power of radiation emitted by a star. We have seen that, right? তারপর হচ্ছে recall and use inverse square ratio, যেটা হচ্ছে AS এর waves থেকে আসছে. Understand that an object of known luminosity is known as a what? Standard candle. Understand the use of standard candle to determine distances of galaxies. Okay, this is important. I mean, far away galaxies, you know, it's possible. Right, so that is it. Next হচ্ছে stellar radii. Recall and use the Wien's displacement law. So ওরা দেখছো কি করছে, ওরা কিন্তু ফর্মুলাটা দেয় নাই. They just said that lambda and T are what to each other? Inversely proportional, right? And use the luminosity equation, যেটা last class দেখালাম. So these two. Use displacement law and the Boltzmann constant to estimate the radius of a star. So ওই যে আরটা বের করার জন্য কি লাগবে? টেম্পারেচার লাগবে, লুমিনোসিটি লাগবে, লুমিনোসিটি ডিসটেন্স বের করতে পারো, টেম্পারেচার ওয়েভলেন্থ বের করতে পারো, দুইটা বসালে you can get this, right? So yeah, these are the ones. The last thing that we have right now is the Hubble's law and the Big Bang theory. এটা তোমরা আমাকে বলবো, আচ্ছা আমি কিছু বলবো না, because you have this in your O levels. I want to remember, like, see how far you remember. Okay, so এখানে হচ্ছে, right, so what is the Big Bang theory? Answer বলতে পারলে যেতে দেব. Point of single surface. Redshift. So what does the Big Bang theory again say? That the universe is and will keep on expanding. Single point. Like a small space. No, it has to be one of them, right? Single point.
There was no concept of space before.
Blasted. Why did it blasted? It's suddenly, like, you know, its mass just became too big. What was it feeding on? Okay. I think we get to do a answer for it. Right. So just quickly, what's the Big Bang theory? So the Big Bang theory basically states that the universe came from this place. So this place that I'm going to define right now is a little debated. So universe actually came from this very small, hot, dense size. The one that was prior to this idea was that the universe came from this event where everything just suddenly came into existence. That is actually incorrect. So what we now understand is that the universe was there already, and it was what size? Very small, very hot, very dense, right? And something triggered it, which caused it to start to what? Expand. And that expansion is what's happening right now. So the idea that the universe formed suddenly, right? It's no more true. The universe was already there. It was there in a what state? A very dense, hot, small state out there. And then something triggered the process, and all the energy and mass just came out and started expanding. And we are still in the part of the expansion process. It's an analogy. It's very, I think, useful analogy. Think of a bottle of Coke. What would the liquid there be? Stable, like in the bottle, like that. Let's say you shake the bottle, right? And you shake it so much that it explodes. That explosion is what? The Big Bang. Did the Coke bottle come into creation and existence because of the expansion, or was it already there? It was already there. So that's the idea right now, that the universe was already there. The expansion is the Big Bang event, and that happened because of some trigger. And the expansion of you know, the Coke goes everywhere and falls everywhere. What starts forming in the Coke? Effervescence bubbles. Those bubbles that you see are galaxies and stars. So at the future, at one point, right, the universe will come to a stable state. What will disappear from the universe? All the stars and galaxies and heat and light and everything. It's called a cold death, that the universe will just become flat. Nothing, there'll be no light out there because the light disappeared. There's nothing to produce light anymore. Okay, so that's the event. We are part of the what process? Like our existence, that bubbling process. We're just bubbles out there. So bubbles will in terms of galactic space reference, takes billions of years to form and disappear. From protect the star form, they die, right? and with like an explosion. That's like a bubble formation, basically. Okay, so that's what we know. Now, recently there have been many theories out there regarding what is actually happening before this. So a couple of ideas out there. One is that এরকম অনেকগুলো exist করে, and we're just part of one of them, right? Or the thing is that the one that's currently very well accepted is very strange. ওটা কি বলে? ওটা বলে যে universe expand করতে থাকবে, and it keeps expanding, like, you know, what's happening right now. Expand করতে করতে একটা point reach করে, and this has been proven mathematically, by the way. একটা point reach করে when the edge of the universe, like the part that's expanding, has the same feature as the initial state, and ওই point থেকে এই পার্টটা আবার কি করা স্টার্ট করবে, expand করা স্টার্ট করবে. It's basically a cycle. So the universe keeps expanding. It keeps expanding so much that the edge of the universe now has the same properties as the original universe, like the small dense part. And we can take our key kora start for it, expand kora start for it. It keeps happening. So it is mathematically proven. There's a person called Roger Penrose. He got like his Nobel Prize for this. And most astrophysicists say they don't understand this, but he understands it very well. He used geometry to explain this, the shape of how universe expands. Anyways, we are very far away from that idea. We're still at the point that the universe is what right now? Expanding, right? So যদি universe expand করতে থাকে, what if we reverse that video? Wouldn't it contract? And that's what we did. We saw the rate of expansion right now, and we reversed it. And as we kept reversing this, we found that it will take around 13.6 billion years for it to go where? The small stage. And that's what we now understand is the what of our universe, the age of our universe. Okay. Aage bolchi, these are all, now at this exact moment not accurate, but on the syllabus it's still the same thing. Okay, so that's the Big Bang. Now, what's the evidence out there for the Big Bang? Number one, we see every star and galaxies out there undergo a what shift? Redshift. What's a redshift? Right, what's this phenomenon known as? The Doppler effect. So Doppler effect states that when a source is moving away from an observer, related to an observer, it undergoes a shift in wavelength, perceived shift. And if it's going away from you, there's a longer wavelength. If it's coming towards you, it's a shorter wavelength. When we look at every star and galaxies out there, right, we see that they have a bit of what in them? Redshift. And not only that, we find the further they are, the more what they are, redshifted. In fact, we have now found galaxies that have redshifted so much that they're not what anymore? Visible, because their redshift has taken them beyond the red part of the spectrum to what part? Infrared. And that's the reason why we sent a telescope recently called the James Webb Space Telescope. What a light that can have infrared, because infrared there's so many things out there we never saw them before, right? So yeah, that's the evidence the universe is expanding. There's something else as well that I can mention, so we won't go into it. It's a little difficult to understand. Cosmic microwave background radiation. That's also a remnant of the Big Bang. মানে একটা বিগ ব্যাং ইভেন্টের পরে একটা সার্টেন ওয়েভলেন্থ রিলিজ করা হয়েছিল, which is still out there floating and flying through space. That's the cosmic microwave background radiation. Okay, so there are many evidences for the Big Bang. It's not like one out there. Okay, so yeah, that is the Big Bang theory. Now, to wrap this up, একটা জিনিস দেখাবো তোমাদেরকে। তোমাদের O levels এ ছিল তো এটা, like I was doing astrophysics with the O level batch just last week. তোমাদেরকে যেটা বলতেছি exact same thing in more details actually. So the question is, why do we have it again? So they want you to focus on this thing, jeta hocche this graph here, which is the graph for the velocity at which galaxies are moving, v meter per second, to how far they are. And how do you find the velocity of a galaxy moving away? Doppler shift use for it. So there's a formula out there which is change in lambda, the amount your wavelength changes due to Doppler effect, by lambda is equal to the speed of your galaxy, recession velocity, divided by the speed of light. A formula so a formula this wavelength represents the wavelength you're supposed to see from a star, which is hydrogen red color, and this is the shift in wavelength. So to me, shift or a wavelength the formula what does that tell you? How far your galaxies are moving away. The faster they move, the greater the shift, right? So আমরা যেটা করছি, we found the velocity and we found the distances. Edwin Hubble is the person, and he started plotting them. There's a famous graph that he did. Back in the day, we only had 10,000 stars and galaxies mapped out. At this moment, we have over trillions of them, right? And he did a graph, and he found that the graph gave you this kind of a graph, where what do you think is the relationship? It's not only like proportional, it is actually directly proportional. It's a straight line passing to the origin. And from there, he came across this relationship V equals to H naught D. V is the velocity at which your galaxy is moving. D is what? The distance, how far they are. And H, a very controversial quantity, is called the Hubble's constant. Controversial because এটার current value হচ্ছে debated. এটা হচ্ছে 2 into 10 to the power minus 18 per second is one of the values out there with an uncertainty of 400%. মানে হচ্ছে it's 400% uncertain, obviously. That's what it means, right? But we're still okay with it. You know why? Because it means that this number could be 4 times more or 4 times less. 4 times more হলে কত হবে? 8 into 10 to the power what? Minus 18. Or 4 times less হলে কত হবে? 0.5 into 10 to the power minus 18. As an astrophysicist, I think I might have mentioned this. What don't we bother about? The value here. Because আমাদের হচ্ছে the main thing that we focus with in space is the magnitude of power. A powerটা কত? কারণ এটা 10 to the power minus 18 is a big information. এটা 1 into 10 to the power minus 18, like 2 into 10 to the power minus 18, which is like 200% wrong. Doesn't really make much difference for us. Okay, so you'll find astrophysics and most of the quantities they have astronomical uncertainties, like really large uncertainties, right? But we're fine with it because power টা matter করে। Power যদি চেঞ্জ হয়ে যায়, যদি একটা থাকে 10 to the power minus 18, আরটা থাকে 10 to the power minus 15, that's a big problem. কেন? এইটা মানে the universe is 13.6 billion years old. এইটা মানে হচ্ছে universe is only 9 billion years old, which is like after the sun formed. So that's a big discrepancy, right? So the ওইটাতে problem হবে. Unfortunately, এই problemটা হয় নাই. We have found value of Hubble's constant independently সবাই, like many people. I think 20 different values. All of them have what power? Minus 18. যেটা vary করে is coefficient, the number in the front. ওটার জন্য universal age অনেকে বলে 15 billion, 16 billion, 13 billion. So the average is 13.6 billion. Okay, so this graph is very important. It's called the Hubble's law, V equals to HD. Now remember I told you that there's a way to find the distance of galaxies now. What do I do to find our distance of a galaxy right now? Let's say you spotted a galaxy, you want to know how far it is. Tell me the process. Yeah, find the velocity. How do you find the velocity? You look at the wavelength, you find the shift in the wavelength, and then use this formula to find how fast the galaxy is moving. And then you go to the graph here, and now you know the velocity. What do you correspond that to? That's it. It's as easy as that. Okay. Back in the day, a 10,000টা বের করার জন্য কষ্ট হয়েছিল। ওইটা আমরা বের করছি কি ইউজ করে? Standard candles and parallax methods and stuff like that. Okay. So yeah, that is more or less astrophysics. This is the graph out there. আমরা হচ্ছে Saturday we'll do like a full recap of this. By that question paper I told you, unit paper 5, topic wise, right? So ওইটা আমরা করা start করব next week থেকে. Okay. Very fast. Some of them have actually now started traveling faster than the speed of light because the space is expanding faster than the speed of light. They're not really going at the speed of light. I'm just speed of the speed. It's the fabric of space in there. Do you know what a travelator is? Airport escalator থাকে flat দাঁড়ায় থাকলে তোমাকে নিয়ে যায়। তো আমরা ওইটার স্পিড বের করতেছি। দেখলে মনে হয় মানুষটা যাচ্ছে ওই স্পিডে, বাট মানুষটা কি যাচ্ছে? মানুষটা দাঁড়ায় আছে, রাইট? তাহলে কিসের স্পিড পাচ্ছ তুমি? ওই নিচের ফ্লোরটা, ওই ফ্লোরটা স্পেস, মানুষটা হচ্ছে গ্যালাক্সি। ওকে, no, it's just the fabric is changing. It's not like they're literally traveling at the speed of light. Their speeds are normal. Maybe we are traveling faster than the speed of light to some other part of the universe. It's a reference point thing. It only allows us to find how far the things are. Next week. Paper 5. So 21, 22, 23. All variants, right? I think you can just do 1 and 2 because 3 and 1 are same. Spring analogy and